Hello everybody, hope you're all doing well. This is the first video for section 3.2. It's on exponential and logistic modeling, so let's jump right in. So to begin with here, you will see that we have this basic exponential population model right here, and that's what we're going to be using for most of our problems today. You've got a population P that's changing at some constant percentage rate per year, that's R. So maybe the population is increasing at 20% per year, so R would be 0.2. Maybe it's decreasing at 10% per year, so R would be negative 0.1 if that's the case. This P sub 0 here, that's the initial population. And R is expressed as a decimal, and then T is time in years. If your R is greater than 0, then this is a growth function. And if R is less than 0, then it is decay. So you need to fill in some blanks there on your notes. Let's see, PO is the initial population, R is, actually that is left off of here, let's add that in, R is the rate, sorry about that, expressed as a decimal, and T is time in years. If R is greater than 0, then 1 plus R is growth factor. If R is less than 0, then 1 plus R is the decay factor for that population. So first, we just have some simple examples here. Let me get to my next page. There we go. It says, tell whether the population model is exponential growth or exponential decay, and find the constant percentage rate of growth or decay. So remember, whatever is being raised to the power here, that is your 1 plus R. So in this first one, 1 plus R is equal to the 1.025. That means that R, if you subtract 1 from both sides of that equation, would just be 0.025. So that is a 2.5% growth rate. However, if you look at the second city here, Mountain View, here the 1 plus R is this 0.92. So that would mean that R is 0.92 minus 1. You're subtracting 1 from both sides, which would be negative 0.08. That is a negative 8% decay. Whenever R turns out to be negative, you have a decay situation. Positive is growth. Now, this one is not on there, but I would like for us to add it. There's one other one I want to do, so just add in letter C there in the bottom margin. What if you have y equals 4 times e to the negative x over 4. Oops. Now, this one's a little more weird here because it's hard to tell what's being raised to the power. Remember, on these first two, it was always, an initial value here times something to the t power. Here I used x instead of t, but same situation. So what I need to do is kind of rewrite it in the form that this was in up here. So I'm going to write this as y equals 4 times e to the negative 1/4 to the x. See how I pulled that x out of that exponent there? And certainly when you raise a power to a power, you're just multiplying those exponents. So negative 1/4 times x is negative x over 4. Now, this right here is your 1 plus r. So then I would write just like we did before, 1 plus r is whatever is being raised to the x power. Sorry, that's my dog. Okay, I'm back. Whenever my dog sees an animal on TV, he barks. So that may happen periodically. All right, so anyway, we have 1 plus r equals e to the negative 1/4. So therefore, r would be e to the negative 1/4 power minus 1. And I'm just going to put that into my calculator. The E button, you should be able to find that on your calculator, raise that to the negative 1/4, and then subtract 1, and you're going to end up with negative 0.22. So this is a negative 22% decay because it's negative. So your R value is negative 22% there. Also, keep in mind that for an exponential growth curve, like this one up here, you know, your basic graph is going to look like this, whereas an exponential decay, your basic graph is going to look like that. We talked about that in the previous section. Let's look at number 2 here. It says determine the exponential function with the initial value, p initial equals 12, and it's increasing at a rate of 6% per year. So keep in mind our basic formula from the previous page. And then you're just plugging in the values that they give you. The initial population is 12. It's increasing at 6% per year, so that's R, 0.06 to the t power. So it's just simply P of t equals 12 times 1.06 to the t power. And that's all there is to that one. Pretty straightforward. Okay, let's look at number 3. This is where we're going to have to do a little more work. We have a culture of 100 bacteria put into a petri dish, and that culture doubles every hour. Predict when the number of bacteria will be 250,000. So to begin with, let's figure out where we put this 100. That's the initial population of bacteria. So that's going to go in right here for P initial. So let's just write that down. P initial is 100. Now, the rate of increase. Notice that it says that the culture doubles every hour. Now, by the way, earlier I think we mentioned that T was the number of years. We were specifically talking about years though, but in this problem we're talking about hours, so we're going to make T the number of hours instead. So if it doubles every hour, that means that the rate of increase is 100%, because at the end of every hour you have 100% more than what you started with. It doubles each hour. So instead of 100%, we would just put 1 for that, which means that 1 plus r is 1 plus 1, or 2. So that's what's going to go in here for 1 plus r. So that gives us our basic function. It's P of t equals our initial value, 100, times 1 plus r, which we said was 2, to the t power. Our question is, when is the number of bacteria going to be 250,000? So what I can do is I can come over here and put 250,000 in place of P of t. To solve for t here, the first thing we're going to have to do is divide both sides by 100. that gives us 2,500 equals 2 to the t. Now, right here is where we have to solve for this exponent, and when you're solving for an exponent, you have to use logarithms. I know we haven't talked about logarithms in this chapter yet. However, you did deal with them last year in Algebra 2. You probably have dealt with them in maybe chemistry class or something. So hopefully we can get through this part without too much trouble. So what you just want to do is take the log of both sides. And I'm just going to do natural log. You can do log base 10 as well if you want to. I'm just going to use natural log every time to keep it simple. So that gives us the natural log of 2,500 equals. Now, you may remember this property that if you are taking the natural log of something to a power, you can take that power and move it out front. That's why we take the log of both sides, because doing that gets that exponent or that variable out of the exponent. And we'll talk about in a later section, we'll review why that is the case, but for right now, just kind of accept it and move on. So then now that I've done that, I can say that t is equal to the natural log of 2,500 over the natural log of 2. And then just put that into your calculator, and you should get about 11.287. And remember, we were doing t in hours, so that would be our result there. Now, alternately, you could solve this problem also graphically. If you're going to solve it graphically, then what you would do on your calculator is you would graph, first of all, the initial function that we came up with, which is y equals 100 times 2 to the x. And then separately in your y2, you would graph y2 equals 250,000. Graph both of those, find the intersection point, and you see that that intersection point is at that same value we had before, that x equals 11.287, or actually I should have rounded it up to 0.288, I guess, hours. So you can do it that way as well. You will have to watch your window. Notice my y max needs to be bigger than this 250,000, so you're going to have to go way up on your y max there in order to find that intersection point. So that's just another choice for that. Again, you would put this in for y1 and this in for y2. Our calculators that we're using don't have this notation here. So that's solving it graphically. We're going to end this first video right here. After watching this, you should be able to do in your note or in your homework packet on pages 4 and 5, numbers 1 through 8. So do those at this time. Thank you. See you later.